In science, the words work and power have slightly more specific meanings than how we use those words in everyday conversation. This is day 1 of lessons 9 and 10 on work and power. When students come into the classroom, the first thing you will do is get into IXL. Remember to do that. Open Schoology, click on the waffle, and then click on Clever. You'll get into IXL and you'll type this code first, 8R6. You're going to practice Newton's laws of motion for about 10 minutes, and then after we practice the Newton's laws of motion, we're going to have a check for understanding. So make sure you get as many of these problems done as you can and ask questions if you're not sure about something. Start with 8R6, which is Newton's laws of motion, then go to ZP7, predicting forces using Newton's third law, and finally Q8X will help you practice about balanced and unbalanced forces. If you are at home or watching this video somewhere not in the classroom, please pause for about 10 minutes or until you've finished the practice problems, and then you can start the video again. So you've done IXL, and we're going to have a quick review of the formative that we recently had on weight versus mass. That was a Venn diagram. We'll have some quick refreshers about the 3 laws of motion, and then you'll have a check for understanding. In class, we're going to lift an object straight up from the ground, and we're also going to drag an object, that same object, up different ramps, some steeper and some less steep. And we're going to think about whether a simple machine like a ramp helps us to do work more efficiently. Here's our learning target for today. I can measure the work and power needed to move an object a certain distance. We will compare forces required using simple machines and without using simple machines. I will know I have gotten it when I am able to use my data to calculate work and power. So from our last check for understanding, we had a Venn diagram where we had to drag ideas to whether they are talking about mass or weight or both. And so these were our most missed concepts. So what is a physical property? A physical property is just a characteristic of matter that can be observed or measured without changing its chemical makeup. So it's going to include properties like mass, volume, color. So the volume of an object is always the same unless you do something to it, right? The color is the same unless you do something to it. The mass is always the same. So mass is a physical property. It doesn't change. Weight is not considered a physical property for us right now because weight changes depending on its location. If I weigh an object on the moon, it will have a different weight from its weight on the Earth. That's because gravity is different on the moon than it is on the Earth. But its mass does not change. Mass is a physical property. Then another idea, what is force? Remember, a force is just a push or a pull. It can change an object's direction, but it doesn't have to. And gravity is the force that pulls objects toward the center of the Earth. Or there's gravity on the moon that pulls objects to the center of the moon. So gravity is a force. We call gravity weight. We call the force of gravity weight. So if we're talking about the weight of something, we mean how many newtons of force is being applied to that object as it is being pulled to the center of the Earth or whatever object it is on. All right, and so just a quick practice of Newton's second law. Newton's second law is force equals mass times acceleration. So force equals mass times acceleration. That's our formula up here. And our problem has lots of words. We're going to read through them. A student sets a 0.4 kilogram soccer ball on the ground and gives it a hard kick. The ball travels a distance of 37 meters. The acceleration of the ball was 2,550 meters per second squared. Based on the data, how much force in newtons did the student apply to the ball? Up here again, force equals mass times acceleration. We need that information because we are wondering how much force did the student apply to the ball. So if I want to find force, I just need mass and I need acceleration. Take a look at your problem. Which one of these values is giving us the mass? A student sets a 0.4 kilograms soccer ball. That's it right there, 0.4 kilograms. That is our mass. Sometimes in a problem, it will say the mass of the soccer ball was 0.4 kilograms. If it doesn't use the word mass in the problem, you're looking for something that has grams or kilograms or milligrams, picograms, nanograms. You want to have that word gram in there, that's talking about mass. So we know our mass is 0.4 kilograms, and if I look at my formula, the next thing I need is acceleration. So I keep reading. The ball travels a distance of 37 meters. Is 37 meters acceleration? No, that's just distance, right? So that doesn't help me right now for this problem. The acceleration of the ball was 2,550 meters per second squared. Right there, that's my acceleration. It even told me in the problem that that was the acceleration. So I now have mass and I have acceleration. Force equals mass times acceleration. Just going to use a calculator and multiply those together. So mass times acceleration, in this case, 0.4 times 2,550. The number is going to be 1,020. And then my force, my units of force are going to be newtons. So 1,020 newtons of force. All right, quick refresher because you're going to have a check for understanding very shortly. Newton's first law of motion is inertia. So this word is inertia. It's spelled I-N-E-R-T-I-A, inertia. That is the Newton's law that says that an object in motion will stay in motion, or an object at rest will stay at rest unless acted upon by another force. So it's resisting change. It just wants to keep doing what it's doing. Newton's second law of motion, that's the law that says force equals mass times acceleration. So force depends on mass and acceleration. As force increases, acceleration is going to increase. So another way to think about this is something heavier or something that has more mass is going to take longer to get moving. Newton's third law of motion, that's the one about opposites and equals. It says for every action there is an equal and opposite reaction. Forces come in pairs. So you're going to have one force maybe moving upward at 27 newtons, and there will be an equal and opposite force. So equal, it'll still be 27 newtons, but if our first force was going up, the second force is going to be going down. All right, so for our check for understanding, you're going to go into Schoology, go to Unit 1, and scroll on down until you're in the blue Formative Assessments folder. You'll click in. Please make sure that you read questions fully, look at your answer options, and choose the best answer. After you finish your formative, you can go back to IXL and work on any of the activities you didn't already finish this morning. So if you are not in the classroom, if you are working on these slides at home or somewhere else, if you need extra time, you can pause. Otherwise, we're going to continue moving on. If you are in the classroom, of course, we are going to have a 12-minute timer to get our formative done. So this is Work and Power. Today's vocabulary. We have a lot of math formulas, so I'm going to show them to you and talk to you about them. You don't have to write anything in your notebooks just now. I just want to talk a little bit about these formulas and the concepts, and then we'll have a demo, and then you'll get to practice doing some math. Work itself, in science, it's the force acting through a distance in the direction of a force. So kind of an easier way to think about this, because that's an awkward statement, the force acting through a distance in the direction of force. Think about it this way. Work is done on an object when a force causes the object to move a distance in the same direction as that force. Power is just the rate at which work is done. So once you determine that work is being done, and you want to use the science version of that, once you know that work is being done, you want to know how fast is it being done. That'll be power. That's the rate at which work is done. And simple machines are basic mechanical devices that can make our daily tasks easier. They can help us require less force to get our work done. Okay, so work is being done on this box if that box is moving. This person is applying force to the box. If the box is moving in the direction of the force, then work is being done. Just a quick reminder of simple machines. We're not really going to spend a lot of time on this. A pulley is a simple machine, a lever, wheel and axle, a wedge, an inclined plane, which we will use today, and of course that's just a ramp, and a screw. Those are all simple machines that can be combined and put together in more complex machines that will help require less force to get things done and make our lives easier. All right, so again, you're not writing this in your notebooks just yet, but we have a lot of formulas that we're going to use in 8th grade science, and so it is important to understand the formulas, and units matter. So later on, you'll be writing these in your notebooks. Okay, force we already talked about over the past several days. Force is mass times acceleration. We know force is measured in newtons. So we'll use the capital N. Capital N, Newton was a guy, it's capitalized. Mass, when we do force is mass times acceleration, mass is always going to be measured in kilograms for this problem. Okay, for us to find force in newtons, we have to have mass come to us in kilograms, and then acceleration is going to be meters per second squared. This is metric. These are metric units, and these are the units that you need to use in order to get newtons. If we want to calculate work is force times distance. We already know force is going to be in newtons. Once we multiply newtons times meters, newtons times distance, we will get work. Work is measured in joules. That's a capital J for a guy, Mr. Joule. Distance for this problem is going to be measured in meters. If we are calculating power, power is just work divided by time. We measure power in watts. It is also named after a guy, but for some reason we don't capitalize it. All right, I'm going to divide watts by time, and my time has to be measured in seconds. So this is important to know because a lot of times you'll get problems in minutes, and you just have to convert. Okay, so take a look at this. If you're in the classroom, you'll talk with people at your table. What are you seeing in these pictures? What do you wonder? So turn and talk, and then we're going to have people share out. If you're at home, you can pause. All right, so in class, we had people talk about how I have a man lifting up a barbell that has weights on it, and so we think he's probably strong, right? We have a man pushing a box, and we can see that this is using force, pushing in the direction to the right, and perhaps the box has moved that whole distance that's listed there. So if we apply a force, we might be able to move something. Right here, I have a trebuchet. We are throwing pumpkins. These are all pumpkins that are in the trebuchet, and that is being, it's a machine that's being used to send pumpkins somewhere. So I wonder, how heavy are those pumpkins? How hard is it to throw them? How much force do we need? I wonder how heavy is that barbell up there? So knowing that we're going to talk about work and power, I'm wondering how all those words connect. Sorry, I was on mute. What is work? Work is the transfer of energy to an object by using a force. Work is done when a force is applied to an object, and that force causes the object to move in the same direction as the force. So if you push a book against a wall and it's not moving, it's just being held against the wall, no work is being done. there's no distance, right? Work is force times distance. If distance is 0, whatever your force is, it doesn't matter because force times distance, force times 0 equals 0. 0 work. What is power? Power is just the rate at which work is done. It basically tells us how quickly work is being done. So if you and your friend both move the same box, but you do it faster, you have more power. If we look at this picture on the left, I have two people at the gym. This guy has raised his barbells all the way up above his head. This guy has only raised the barbells up to maybe even shoulder height. Okay, we're assuming it's the same weight. Which one is doing more work? It's this guy because he lifted the barbells up further. So if work is force times distance, we know the force is the same because force is weight, or in this case, weight is force. Same force, but this is a greater distance, so he did more work. For these two athletes, he has a heavier barbell, a heavier weight than this one. Okay, they've gone the same height. They're both all the way up to that high, same height, but because this weight is heavier and work is force times distance, this guy does more work. So looking at the examples below, we want to think, is work being done? Remember, work is done if you apply a force and you move an object some distance in the direction of the force. If I push this box to the right and the box moves to the right, am I doing work? Yep, I am. Direction of force and movement. If I am applying an upward force to that backpack so it doesn't fall onto the floor, but I'm walking forward, am I doing work? No, whoopsie, sorry. No, because the direction of the force is upward, but the movement is forward. In this case, I'm going to lift a bag of groceries up. So I'm applying force and lifting up, and I'm raising up that bag of groceries. So yes, we are doing work. My gosh, sorry. We are doing work because force and motion are in the same direction. And finally, I've lifted my groceries already. Now I'm holding them up. So I have to apply an upward force to keep them from falling to the ground, but I start walking forward. No work is being done here because I'm applying a force going upward, but I am moving forward, not in the same direction. Okay, so humans use energy to power machines, and those machines make work easier. So from moving a 2-ton shipping container onto the back of a freight truck to using robots in factory assembly lines, humans look for ways to move or stack or shape the natural world in the most energy efficient way possible. To use energy more efficiently, humans do sometimes use simple machines. All right, so this image is going to show you lots of different simple machines that you can think about. There are 6 main simple machines that we know that are combined to make complex machines that make work easier for us. This dolly has an inclined plane that's going to help reduce the amount of force required, plus it has wheel and axle. Our wheelchair also definitely has wheel and axle. We have wheel and axle on the bicycles. We have wheel and axle on the skateboard, and on occasion that's going to be an inclined plane. And if you look here, we have a ramp. So this inclined plane or ramp will actually require less force for people to get up and over to the sidewalk. So just a reminder, we do use simple machines, and those help us reduce the amount of force required so that we can make life easier. In class, we used an inclined plane like this, and we dragged a mass up along that inclined plane. When we use the spring scale, we can calculate how much force is required to drag a mass up along the ramp. And so we actually set our ramp at 5 different heights. We set our ramp at 0.1 meters, and then at 0.2 meters, and so on, 0.3, 0.4, 0.5. So in class, we had a pretty shallow ramp, and then we made it steeper. Each time we pulled our mass up along that ramp and measured the number of newtons required using a spring scale. Also, we just went straight up and down with our mass. We used that spring scale to see how much force was required. And since there was no simple machine, it was just lifting the object straight up, the force was always the same. And we did a different amount of work depending on how far we moved our object. So again, we moved up to 0.1 meters, and then 0.2 meters, and then 0.3 meters, 0.4 meters, and finally 0.5 meters. So in class, we had a demonstration of this, and we have some videos in Schoology that you can access if you want to see what that looked like. So last class, when we did that, we actually filled in information this class, we're going to fill in information about the distances we are moving our object. So without a simple machine, we're just pulling the object straight up. So we pull it up 0.1 meters, and we look on the spring scale. What is the force pulling down on that object? It's just its weight. And so we realized we were going to use the same distances for our simple machine as well. For our force coming straight up and down, it was 3.2 newtons. That was our mass of in a baggie that we hung from the spring scale, and the force of gravity on that mass was 3.2 newtons. Okay, because we are not using a simple machine, and so the weight of the object is not going to change in this case because we're still on Earth the whole time, every one of these values for force is going to be 3.2. It's 3.2 newtons every single time. But the work is going to change because work is force times distance. So if I'm calculating work right here, force is 3.2 times distance is 0.1. I'm going to get 0.32 joules. When I pulled that mass up the ramp at my different heights for the ramp, the shallowest ramp, my force was only 1.2 newtons to drag that object up along the ramp. And you can imagine as we get steeper with our ramp, we're going to require more force, and that's what we found. Next time, when our ramp was a little bit steeper, it took 1.6 newtons to drag that force along there. Then it was 1.8 newtons. Even steeper, we have 2 newtons of force required. And finally, it took 2.2 newtons to drag up our steepest ramp. So it's the same object with the same mass, but our force of weight, when we just lift it up vertically, is always going to be 3.2. Our force required to move it along a ramp depends on how steep the ramp is. So we're going to calculate work in joules for all of these scenarios. 0.1 times 3.2 is 0.32 joules. It took 0.32 joules to move our object up a distance of 0.1 meters. Okay, so this was something I'd like for you to do. You may use a calculator. You do the math on all of these problems, and we'll check work later. This will be homework if you don't finish it in class. You're going to calculate work for all of these open boxes. Remember, here's our formula right up here. Work is force times distance. Okay, and then we'll continue on with day 2. You can watch that video after we have our day 2 lesson. We actually filled in information this class, we're going to fill in information about the distances we are moving our object. So without a simple machine, we're just pulling the object straight up. So we pull it up 0.1 meters, and we look on the spring scale. What is the force pulling down on that object? It's just its weight. And so we realized we were going to use the same distances for our simple machine as well. For our force coming straight up and down, it was 3.2 newtons. That was our mass of in a baggie that we hung from the spring scale, and the force of gravity on that mass was 3.2 newtons. Okay, because we are not using a simple machine, and so the weight of the object is not going to change in this case because we're still on Earth the whole time, every one of these values for force is going to be 3.2. It's 3.2 newtons every single time. But the work is going to change because work is force times distance. So if I'm calculating work right here, force is 3.2 times distance is 0.1. I'm going to get 0.32 joules. When I pulled that mass up the ramp at my different heights for the ramp, the shallowest ramp, my force was only 1.2 newtons to drag that object up along the ramp. And you can imagine as we get steeper with our ramp, we're going to require more force, and that's what we found. Next time, when our ramp was a little bit steeper, it took 1.6 newtons to drag that force along there. Then it was 1.8 newtons. Even steeper, we have 2 newtons of force required. And finally, it took 2.2 newtons to drag up our steepest ramp. So it's the same object with the same mass, but our force of weight, when we just lift it up vertically, is always going to be 3.2. Our force required to move it along a ramp depends on how steep the ramp is. So we're going to calculate work in joules for all of these scenarios. 0.1 times 3.2 is 0.32 joules. It took 0.32 joules to move our object up a distance of 0.1 meters. Okay, so this was something I'd like for you to do. You may use a calculator. You do the math on all of these problems, and we'll check work later. This will be homework if you don't finish it in class. You're going to calculate work for all of these open boxes. Remember, here's our formula right up here. Work is force times distance. Okay, and then we'll continue on with day 2. You can watch that video after we have our day 2 lesson.